All right, today we're going to talk about, or actually, so we talked about gases previously. Now we're going to talk about liquids and what kind of holds liquids together and what properties what properties do liquids exhibit. And so before we talk about liquids, we have to talk about what's called intermolecular forces. And so this just talks about the difference between intramolecular and intermolecular. So intra means within, whereas inter means between the molecules. So we've talked about intramolecular forces. They're the bonds that hold a single molecule together, ionic, polar, covalent, nonpolar, covalent, metallic. And then intermolecular forces, those are forces between the molecules. So we can call them London dispersion forces, dipole-dipole forces, or hydrogen bonds. Those are the three that we'll go over today. But before we start, we need to talk about, I think maybe something's out of order here. So what we need to talk about is polarity. So in terms of intramolecular forces, we have two types of covalent bonds, nonpolar and polar. And so if you remember, nonpolar covalent bonds is when they're, so covalent means to share, right? So when you're sharing your valence electrons. However, nonpolar means it's an equal sharing, right? And then polar covalent means not equal. Okay, and so let's just do an example. So remember, equal sharing has to do with the electronegativity. So electronegativity is the amount of pull that an atom has on valence electrons. So if we have chlorine with chlorine, so Cl2, which is diatomic, right? There's a bond between the two, right? And so if you remember, because chlorine has electronegativity of 3, that means they're pulling on this valence electron. Now remember, a bond is just a shared valence electron. So now instead of, I'm going to put chlorine there, okay? All right, I'm going to put this shared pair of electrons. Since both chlorines are pulling or have the same electronegativity, the electrons stay in the middle and they're shared equally. Now, with polar covalent, let's just take the example of hydrochloric acid, so HCl. You'll notice that hydrogen and chlorine share a pair of electrons. However, chlorine has an electronegativity of 3.0 and hydrogen has an electronegativity of 2.1. So what you'll notice is that the electronegativity here is quite different. The difference is 0.9. Who's pulling harder is the chlorine. So these electrons, actually, instead of in the middle, they kind of move slightly over here towards chlorine. So this will make chlorine slightly negative. So this means partial, so partially negative. Why? Because it has more electrons closer to it, and makes the hydrogen slightly positive. So this is what a polar molecule, it has a slightly positive and a slightly negative part. Okay, why? Because they're not sharing, or sharing unequally. All right, now this is just intramolecular, right? So this is what's happening within the molecule. But let's talk about intermolecular. So these intramolecular, polar, nonpolar, covalent is necessary to understand an intermolecular force. There are 3 intermolecular forces. The first one we're going to go over is London dispersion forces. London dispersion forces, they occur between nonpolar molecules. So let's take our example of chlorine. So when I when we're talking about in these intermolecular forces, I want you to remember those are the forces between these two molecules, right? We just went over the intramolecular. That's the forces within a single molecule. So remember, since these are nonpolar molecules, they share those electrons. So let's look at one. Now, what you have to know is these electrons, they are not static. I mean, they're not just chilling there, hanging out. They actually move, but they kind of move back and forth. And so sometimes these electrons will move this way, or sometimes they'll move that way. They just kind of like go all over the place. They're not static. And so when that happens, and it's a random thing. It's not like it's not intentional or it's attracted towards one more side or the other. They just move. And so when they move, what happens is, like let's say at a particular moment, this chlorine these electrons move over here. At this moment, you will have what's called a dipole because you'll have a slightly negative and a slightly positive, right? Remember, this only happens in a moment. So then what happens is, and then let's just say randomly, this over here, these electrons move over here just for a moment. So now this becomes slightly negative, this becomes slightly positive. What I want you to see is there will be a slight attraction with this negative and this positive for this moment. So this will be very temporary. This will happen, and then the electron will move back, and then that connection will be lost, right? And so why is this so weak? It's because this is temporary. There's an attraction between the negative and positive form, but it just happens and then it's done. And so London dispersion forces are the weakest, and they happen between nonpolar molecules. All right, let's talk about some ones that are a little stronger. Dipole-dipole. So this occurs between polar molecules. And so let's talk about the polar molecules so here we have HCl. All right, so in this case, remember the electrons are close to the chlorine, why it's more, and this will always happen, right? Oh, that's going to be a negative, isn't it? Now this is permanent, right? So these create what we call permanent dipoles. Like the electrons will always be closer to chlorine. Why? Because chlorine has a high electronegativity. It's attracted towards chlorine. You'll see that this plus and this negative will form these called dipole-dipole forces. So this IMF here is a little more stable and a little stronger. Why? Because these are permanent. I think that's right. So it's not like those electrons will move back towards the hydrogen. Those electrons will stay close to chlorine. Why? Because chlorine's more electronegative, and so you'll get attraction going on here between the hydrogen and chlorine, and so that's what holds them together. And then hydrogen bonds is the last one. It's the strongest. It's between polar molecules, but specifically it's whenever hydrogen is in contact with nitrogen, oxygen, or fluorine. So in the case of water, so oxygen is more electronegative than water, so this is going to be more negative, right? Because why the electrons are closer, this is more positive. And then I did it wrong, I'm sorry. There's two hydrogens, right? So two hydrogens. This is negative. Then we have another oxygen. Less the oxygen's negative, right? And so This is a type of dipole, right? Because you always have plus with minus, right? The positive is always attracted to the negative. This is a type of dipole. It's a special type. Why? Because you have hydrogen attracted to oxygen. So I just want you to see hydrogen bonds are just a special type of dipole. It's whenever hydrogen is attracted to oxygen, nitrogen, or fluorine. In this case, it's attracted to oxygen. This is a hydrogen bond, and it's the strongest. Okay. All right. So let's just do a recap. So we have three types of IMF: London dispersion, dipole, hydrogen bonds. So London dispersion, they're the weakest, right? Why? Because they're temporary. These dipole moments are temporary. Dipoles are the next, I guess, and the hydrogen bonds are the strongest. I guess you could put medium or something. And so these are permanent. So the weakest, they occur between nonpolar molecules. These occur between polar, and then these occur whenever hydrogen is attracted to nitrogen, oxygen, and fluorine. All right. Now let's talk about boiling and melting points. So when something melts, like you guys did yesterday, you're taking something that is solid and really structured, and you're weakening the IMF so that it can move in close proximity. That's a liquid, right? And so if you had a weak IMF, it wouldn't take much energy to weaken the IMF in order to allow the particles to start moving. So in that case, this is lower. They'll have a lower boiling and melting point. Why? Because they're not as strongly attracted to each other, so it's easier to break apart, so then the particles can start moving, that kind of stuff. So your hydrogen bonds should have your highest, and this is medium. Okay, what does this have to do with liquids? Well, because liquids are in close proximity to each other, unlike the gases, IMF plays a huge role. And so we're going to cover these three. I'm going to leave capillary action. If you're in the AP Bio, you want to kind of learn about this capillary action. But I'm going to talk about three things: fluidity, viscosity, and surface tension, and how they relate to IMF. So fluidity is how a substance flows, right? So it's how these particles, how they flow past each other, right? Now just think about this logically. If you have great IMF, so if you had high IMF, that means they were really attracted to each other. What do you think would happen to fluidity? Would the particles be able to flow freely or not flow freely? Well, they wouldn't be able to move as freely, right? And so that would lead to lower fluidity. Why? Because they're kind of stuck next to each other. Viscosity, it's the opposite of fluidity. And so there's three things that affects viscosity. First is IMF. Now think, if it has greater IMF, what would happen to viscosity? Well, we know viscosity is the opposite of fluidity, right? And so if they had a greater IMF or greater attraction amongst each other, they would be more viscous, meaning they wouldn't move, or there'd be resistance to flow or fluidity. The second one is temperature. So as you speed up the temperature, what do you think is going to happen to the viscosity? Well, if you increase the temperature, you're adding more energy to the system, right? And so the molecules are moving faster. If they move faster, they're able to break apart those IMF, and so you're going to lower the viscosity. And the last one is size, the size of the molecule. Bigger things tend to move slower, so the greater the size, the greater the viscosity. Okay? And the last one is surface tension. So you guys did surface tension when you dropped those, the water or solutions on the penny. And remember, it's if IMF is the attraction amongst these molecules, the greater the attraction, the more that you can add, or the more drops you could, or the more molecules you could have added, because they can kind of hold on to each other tightly. And so surface tension is how strongly these molecules hold on to each other. And so if you have greater IMF, you actually have greater surface tension. Okay. These capillary actions you're more than welcome to take a look at. Okay, there's a quick check tomorrow, and there's an ed puzzle for homework.